At 9:17 a.m., my phone started vibrating nonstop. Pager duty fired first, then Slack lit up, then the customer success channel exploded. The alert was simple but alarming. HTTP 500 error rate above 35% across the primary API service. Login requests were failing. Checkout requests were failing. The dashboard showed a sudden cliff. Success rate dropped from 99.8% to barely 60% in under 2 minutes. CPU looked normal. Memory looked normal. Node health was green. The load balancer was distributing traffic evenly. No region outage. No spike in traffic. Everything was green, but users could not log in. We were running in AWS, primarily in US East 1, with a secondary disaster recovery region in US West 2. The production cluster was Kubernetes on EKS, roughly 120 pods across multiple microservices. The core API service handled authentication, billing validation, and session management. We averaged about 4,000 requests per second during peak hours. The backend relied on an RDS PostgreSQL cluster with red replicas and Redis for session caching. CI/CD was handled through GitHub Actions and Argo CD. Monitoring was Prometheus and Grafana for metrics, Loki for logs, and Alert Manager wired into PagerDuty. We also had CloudWatch alarms. Nothing in AWS Health, no node pressure, no failed pods. From the infrastructure perspective, everything looked stable. Users reported they were getting a generic authentication error, not a timeout, not a 404, just a 500. The error message was intentionally vague. Grafana showed the error spike was isolated to the authentication endpoint. Other endpoints were partially functional, static content loaded, health checks passed. That was the confusing part. Kubernetes readiness probes were all green. It returned 200 OK. Kubernetes believed the pods were healthy. But production traffic told a different story. Looking at request latency, it had not spiked dramatically. Requests were failing fast. That suggested an application-level error, not a network issue. The suspicious signal was that Redis connection metrics were flat. Database connections also looked stable. So if dependencies looked fine, why was authentication failing? My first hypothesis was database schema drift. Maybe a migration went out incorrectly. I checked the deployment history. There was a deployment 12 minutes earlier. Minor change. I rolled back mentally through the diff. No database migrations. Just some refactoring around environment configuration handling. I pulled logs from the failing pods. The logs were noisy but consistent. Every failed request had the same underlying exception. It said authentication provider not configured. That made no sense. This was production. The provider had been configured for years. I checked the config map for the service. Everything looked intact, all present. Then I noticed something subtle in the logs. The error referenced a missing environment variable called auth provider secret. It was supposed to be injected from a secret. I ran kubectl describe pod on one of the new pods. Under environment variables, I saw the URL and ID, but the secret was not there. I checked an older pod, it was present there. The new deployment had created fresh pods, but they were missing one environment variable. The old pods still had it, but they were being gradually replaced. I checked the secret. It existed. At this point, I pulled in another engineer. We started comparing the deployment YAML in Git to what was running in the cluster. That was when we noticed a change. In the refactor, someone had renamed the environment variable in the deployment spec from auth provider secret to auth secret, assuming the app would read the new name. But the application code still referenced the old variable name. The deployment updated successfully. The pods were healthy from a readiness perspective, but at runtime, it failed. It did not crash. It just failed authentication requests. Business impact was immediate. Paying users could not log in. Support was escalating. Leadership was asking for updates. We had two options: roll back the deployment to the previous version or hotfix forward. Given the simplicity of the change, we chose rollback. It was faster and lower risk. The root cause was a mismatched environment variable name. The manifest referenced auth secret, while the application code expected auth provider secret. The variable was never injected. The application did not validate its configuration on startup. Instead, it lazily attempted to use the secret during requests. When it was missing, it threw a runtime error for each login attempt. Because the readiness probe only checked a shallow health endpoint, it did not detect the missing configuration. This is why the system reported everything as green. We rolled back using Argo CD to the previous stable commit. That triggered a rolling update of pods back to the prior image and deployment spec. New pods came up. Within 2 minutes, new pods came up with the correct variable mapping. Error rates started dropping. Within 5 minutes, authentication success rate was back above 99%. We verified stability by monitoring error rate, login success metrics, and Redis session creation. We also manually tested logins through multiple regions and user tiers. Total impact time was roughly 18 minutes from first alert to full recovery. A short time, but enough to disrupt thousands of users and put the team on high alert. What actually failed was not Kubernetes, not AWS, not the database. It was configuration discipline. We allowed a deployment that changed environment variable names without validation. Detection was weak because our readiness probe was shallow. It only checked that the HTTP server was running, not that critical dependencies were actually configured. Observability gaps were also clear. We had no alert tied specifically to authentication failure rate until it crossed a high global threshold. We needed more granular alerts. Organizationally, the refactor was reviewed primarily for code logic, not configuration contract compatibility. This was a process failure as much as a technical one. First, environment variables are part of your public contract between infrastructure and application. Changing them is a breaking change that requires careful planning. Second, applications should fail fast on missing critical configuration. If a required secret is absent, the pod should not even become ready or start up. Third, readiness probes should validate critical dependencies, not just process health. Check your secrets, check your database, check your external APIs. Fourth, configuration changes should be tested in staging with automated smoke tests that validate real authentication flows, not just service uptime. We must test real user paths. Fifth, even small refactors deserve production-level caution because configuration drift is often invisible until runtime. Treat every configuration change with high respect. That morning reminded me that sometimes the smallest missing variable can bring down the most stable system. Stay vigilant, test deep, and respect the configuration. In the end, it wasn't the infrastructure that failed, but our discipline. Now we're stronger for it. Keep your system stable and your variables consistent.